And that's pretty much what we can conclude, that TV and radio advertising have significant p-values, while newspaper advertising is not. R-squared of this model is around 90% now. Basically, another way to look at it, so what is interesting in this case, linear regression model automatically tells us pretty much that newspaper advertising is not significant. Yeah? And that's what we can think, how we can use that. So it looks like this linear regression model can tell us somehow which of the features are not important. In this case it says that newspaper advertising is not important. The feature is not significant. And this should continue later on with this line of thinking. So can we do something with our linear regression model that it automatically tells us which of the features are not important? And not necessarily by looking at the p-values or significance, but maybe there is some other way to do it. No, it's called regularized regression. So look at that. So we can also do the same linear regression scikit-learn. Scikit-learn will be our basic package for machine learning. Not much changes. So you import linear regression from scikit-learn. You assign your model to be linear regression. You do the fitting for your data, and after that it displays you the intercept and the slope, and those are the same numbers as we had before. So after that, you can also do it for the TV, radio, and newspaper. You can issue predictions by saying, yeah, that's how much we want to spend on each of the budgets, and so on. You can look at the R-squared, and so on. So the next step is, so far all our features were numerical, yeah? Very easy to work with. So what happens if we have categorical features? So for instance, we have another feature, the size of the market, large or small. And the size of the market which we operate. So now this is the categorical feature. So we cannot stick it into a linear regression as a feature because it only accepts numbers. We cannot stick large or small into there. So what we need to do, we need to, as you know from existing scrolls, we need to convert it into a dummy variable, which can only take the values 0, 1, but it's now a numerical variable. And basically the dummy variable in this case, so what its scope is large, is telling whether we are operating in a large market, 1, or in a small market, 0. So when it's large it's 1, when it's small it's 0. So in this case we can encode the size of the market, so because this we cannot use the feature should be numerical and not some string or a name. So we encode it as another feature called x large, is x large, that's a feature number 4, and we now can put this into the linear regression model as a new feature, representing the size of the market. We run our model and we see that this is the coefficient for the size of the market and how we interpret it. So a large market is associated with an average increase in sales of 151 additional units. So what happens if we have more than one category? So if we have a variable representing the area in which we are selling, rural, urban, or suburban. So 3 categories instead of 2. What do we do?
3 numbers. Yes, 3 features.
So how many additional features we need to introduce?
6. Rural, urban, suburban. One feature.
And both answers are correct. We can either introduce 3 features, but it's enough to introduce 3 features because those are mutually exclusive. So we know if the market is not urban or rural, it's automatically suburban. So this third extra feature is redundant, even so if you want you can stick it. It doesn't hurt. So in this case, and that's also kind of special name. So if you are gonna to use 3 features for this area, it's called one-hot encoding. If you just gonna to use 2 features, which is enough, those are typically called dummy variables. Again, but the third feature is going to be redundant in any case, because we can infer that if it's not rural and not urban, it's going to be suburban. So this first feature is redundant. Everybody with me on that? but it doesn't change the results if you stick the third feature into your model as well. So, but that's the feature is enough, so you can add one feature called area suburban, another feature area urban, and it's automatically, if it's not urban or suburban, it's going to be rural. So we don't need the is rural feature. But if we stick, no problem. That third feature. Again, we run linear regression, we get the coefficients, and basically what it says that being in suburban area associated with an average decrease in sales of 137 units, and being in urban area is associated with an average increase in sales of 242 units. So that's interpretation of the coefficients, which we always need to do. And that's pretty much all for linear regression at the moment. So any questions so far? Yes?
Well, these dummy features, necessary to convert it in 0, 1? It is always necessary? I mean, I cannot keep city, village.
You can pretty much, it can be automated in scikit-learn and stuff like that, but yeah, you still need to basically tell it or encode these features. But it's automatically encode those as 0, 1.
Okay.
You can encode with 9 times any number, right?
You can encode with any number, but in that case, your interpretation is more difficult than 0, 1.
And but you don't want it to be like a series of numbers because you can't have an average of urban and suburban, right? Like it has to be just.
Yeah. Another thing that we didn't discuss. Okay, so now we figured out how to encode categorical features, yeah? Categories. So urban, suburban, whatever. And in this case, the categories are not ordered. What happens if your categories are ordered? So you have, let's say that you have categories for salary range. So first salary range between 0 and 10,000. Second category between 10,000 and 20,000, whatever. And the third category is between bigger than 20K. So 3 categories, but now those are ordered. This is smaller than this, and this is smaller than that, yeah? There is an order in the categories. What do you do to encode those? Okay, let me do it. Let me slightly change the ranges so that 1, 2, 3 would not work. So let's say that this is going to be to 40K, and this is going to be, just to make the interval close, 40K to 100K. How about this? Is 1, 2, 3 still a good idea? Or, because you see what happens here, the distance between this category and this category is not necessarily the same as distance between this category and this category. You need to figure out how to encode this, and there is no unique way. You need to figure out the distance. So here, for instance, you can encode this as 1, and you see, okay, so the average between 10 and 40 is something like, I don't know, maybe I encode this as 3, and maybe I encode this as 6, because here is another range. So, but that's again, that's your idea how you design these distances between the categories. Yeah? Another example which is probably easier to digest is the education level. Let's say you have the categories, you have a bachelor degree, you have master's, or you have PhD. Now, well, how do you encode this category? Those are ordered as well, yeah? In order to get master's, you need to have bachelor. In order to have PhD, you need to have master's. So, how do you encode those?
4, 6, 8 years of.
Exactly. So that's the simplest typical way. Years of studies. Again, but here you have some ideas. Yeah, 4 years typically. Here it's 6 years. Here is 10 years, for instance, of study in total. Maybe less than 10. Maybe you just extract. Maybe you are able to do it at not. Again, but nobody tells you should encode it in years. Maybe it's some other efforts, and maybe years are not consistent between different countries. So you may need to think, basically. That's what it is. As soon as you have ordered categories, you need to think how to convert those into numbers. And there is no unique way. You just need to think what that means and what's more appropriate for your use case.
It's feature engineering.
It's a feature engineering at the end.
Introduction to feature.
Actually, another feature engineering. So basically, anything feature engineering is really starting from a very simple things to go into a very complex thing. So, one very simple rule: all features that we put in our models should be numerical, should be numbers. Yeah, you cannot put strings, you cannot put anything else. Names, you cannot put addresses, for instance. What happens if you have addresses of people in your data set? You have an address. Now, how you encode address as a feature? Again, you need to think.
Split city, street, area.
And there are many ways. You need to think. So what makes sense? For instance, does it make sense? Can a feature be distance between your address and the city center? Potentially. In that case, it's a number. Yeah.
It depends what the goal of the project.
Exactly. It depends on the goal. So can be the distance to center, city center. Yes, can be. Can be a distance to the closest shop.
Elevation.
Of course, can be distance to the closest shop.
Elevation above sea level.
Exactly. Elevation above sea level. Even XY coordinates, longitude, latitude, can be because those are numbers, two features. Can be anything else. You just need to think what's appropriate for use case. Maybe if you are modeling the price of a house, so the distance to the nearest school, the distance to the nearest store, the number of stores within 1 kilometer of the address and so on, all these possible features that explain the value of your house. But you need to think, and that's really feature engineering. All what you have the address. After you need to engineer features that potentially explain the value of your house, the target variable y. Again, we are not touching that much of this in the course, but that's something to think about. Encoding features, engineering features, what features really have explanatory power for your target value. And nobody will tell you until you start understanding the subject area in which you are doing the modeling, until you experiment, until you talk to experts, until you read, until you try in Python, substituting different features, write different models. So that's why, again, data science, AI is not only science, it's also an art, and it's also a business.
So this is the main value, of data scientist.
Exactly.
Because framework is the same, but we have this price of $1 million, so it's yesterday,
Exactly. And the value of data scientist is in thinking and understanding the business side of the problem. Because technical side you can learn. So everybody can learn all these models and understand after some time how those work. But if you cannot look outside of the box, if you're not creative, if you don't understand the business side, if you're not able to think creatively, it's useless. Again, people who mechanically able to run models, value of them on the market is small, and those are going to be replaced by the automatic AI algorithms, which are typically known as AutoML or AutoAI.
It's data engineer, but there is data scientists which...
Typically data engineers are people who work with databases and they prepare data for data scientists. Again, there is a big distinction. So, again, the thing is, they need to be able to think in outside of the technical stuff that they are studying as data scientists. So being the data scientist is not enough. You need to understand the business. You need to be able to think which features make sense. You need to basically understand the subject area to which you apply. Talk to experts, talk to people, see what works, analyze the results, interpret the algorithm. So there are many things, and that's why we are in an interesting area, in my opinion.
I understand that I should try, but theoretically, in this case, if instead of areas, if instead of this adding these two columns, I will add only one column with 0, 1, 2, I will receive another result of the model.
Which column? 0, 1, 2?
Yes, instead of the last two.
In that case, you assume that those are ordered features.
Yes.
And whether those are ordered, I don't see why those be ordered. Even so, you may think about those. First is urban, after suburban, after rural. Maybe you can interpret those ordered. Yes. I know, but I don't see that. But maybe there is a case for that.
Finally, I will receive another result of the model.
Of course.
Okay.
Yeah, so by doing what's suggested here with 1, 2, 3, you're adding weight to a variable?
Yes.
Yeah, you are changing the meaning of your feature in the first case. So then essentially if you put in 1, 2, 3, you're assuming an order.
Yeah.
You know that 1 is more important than 0 and 2 is more important than 1.
Not just yes, no.
Oh,
1, 2, 3.
exactly, which in this case I don't see the case to do it for the areas, urban, rural, suburban. I don't see that order having a meaning. But again, you may have a case, you may have an explanation why that makes sense. But it should make sense.
And if I keep just string,
Urban.
If you keep string, basically the algorithm doesn't understand the string, so feature should be number. If you just reject, say, okay, I can offer the strings, then you put it into.
do I receive message about this error or something?
Exactly.
Okay.
Your vector of, so your feature in every example, so should be a number. So this should be a vector of numbers, and not a vector of strings or vector of any other objects in Python. Okay, so what is? So when is the break? 11:50. Well, just now. Okay, good. Good time to take a break. So feature engineering, think about it. That's important, but nobody will tell you how to do it profitably. That's why you spend not an hour on the project, you spend days figuring out what's going on underneath. Yeah.
Excuse me, but how can we interpret the results if we, for example, have the results as when we use, for example, for rural 0, for urban 1, and for suburban 2? How can we interpret the results of this 2 for suburban? Multiply that by 2.
Or yeah, so but in that case, so you have one coefficient as a result of this feature 0, 1, 2. And you basically assume that the larger is your value of the feature, what to say?
I mean,
It's basically a standard, in that case we apply the standard importance of that coefficient. The value of the coefficient beta means that when you multiply by 0, 1, and 2, or by 1, 2, and 3, it tells you
my understanding of doing 1, 2, 3 for that is because those are not solid distinctions. That a value of like 2.5 is like somewhere in between urban and suburban in terms of like density levels or something. Like, is that
maybe
another way of interpreting what that means?
That's another way, but in that case, yeah, if you interpret it as density, you may put the number into density. Yeah, in that case, you really introduce some order, but you also change slightly the means. So you're now looking at the population density, and it's not necessarily rural, urban, suburban. So you are, in that case, you probably have the feature which is called the density of the.
No, I mean, I'm not saying that like, because you can conceive of something that's half rural, half suburban. Is a number in between those two things, would that equal to that conception of something that's halfway between those two things? If it's about preferences between rural and urban, then you say actually what people do prefer is something that's not quite this and not quite that.
Yeah, but preferences are subjective, you see. It's not something that. Features that you put also can be subjective. So in that case, you're introducing your own subjectivity into this, which is fine. But in that case, that's what you get as a result of your model. And coming back to the question, so let's finish with that clearly. Another important thing in machine learning is the feature importance. So this is something that how important is each feature in our model. So how important is, or in this case, how important is TV, radio advertising, how important is the size of the market, how important is the. So how we can tell, how quantify the importance of the features.
Correlation coverage.
Coefficient size.
Coefficient size. That's for linear regression. How about other algorithms? What is really the importance of the feature? So think, we have the target variable, we have our features, or we have essentially our function. So what is the importance of the feature? importance of the feature is the derivative of our target variable with respect to that feature. Yeah?
Derivative.
In linear regression, it's really a coefficient, because in that case, this is equal to beta 1, yeah? Very easy. But in neural nets, in decision trees, the derivative is not going to be the coefficient, it's going to be something else. But that's really what is the importance of the feature. How change in the target variable, how much change in the target variable can be explained by changing the feature. That's what we mean by importance. That's a derivative. That's what derivatives are for. If the feature is not important, well, so large change in x1 will cause small change in y. Yeah, and the coefficients will be small. That's another thing why maybe for interpretation it makes sense to normalize, standardize our features. Again, that's another thing that is really neglected in many cases. Does it make sense to normalize the range, for instance, of the features to be between -1 and 1, or 0 and 1? So, and the answer in that case would be, okay, it depends on the algorithm. So when you normalize features, it doesn't change the solution. For linear regression, it doesn't. You will still get the same coefficients. But for some other models, it may change the solution. And one example of that is k-nearest neighbors algorithm, which is very simple algorithm. So KNN algorithm, all what you are doing, so you have your data, xy, you have your examples, and the new example comes in. So as here you check to which of the other points is close. So for instance, it's close to these 3 other points. And you assign the target variable. If it's discrete, you do the majority vote. If it's categorical, you just compute the average between the target variables, so it's 3 points, and that would be your output. And in k-nearest neighbors algorithm, when you scale, normalize your features, you change in the solution. So for instance, you have 2 features, x1, x2, and here you have just 1 point. So now you have, how to explain? Basically, when you shrink, then you normalize the features, you change in this distance, and your point may become closer to another point. So you have this point. So now the point here is closer to this, but then you normalize. So this point moves here, and now your point has become closer to that. So that may change the solution. Another something to keep in mind. So we may get to this or not get to this, but you may think about normalizing features, meaning those shrinking those to the same range, for instance, between 0 and 1 for all features. Now there is automatically in the range of 0 and 1, so you don't need to do anything with those.
So logarithmic is the same, sense. When we apply logarithm to the feature, so it's also changing.
Yeah, but logarithm is a non-linear transformation. You see, that's another thing. So yeah, you may do, that's another part of feature engineering, you may apply non-linear transformation to the features. Taking the logarithm. You need to justify why it makes sense. Typically people apply just, so they square, you can square the features, you can multiply the features. That makes more sense, and you need to find the case for that. And actually linear regression is what's really interesting, so you can do this, multiply by x squared. It's still linear regression because you just call it a new feature x2. It's not changing your linear function to a periodic function.
Yeah.
So x squared is another feature x2 and just a column of numbers. So who cares? It's still linear regression. So you may introduce non-linear transformation of the features still within the same model, within the linear regression framework.
In case if we look at the visualization and we see that relations between independent variable and dependent variable looks like
exactly. Yeah, and that's very typical to do. Some models will do it for you automatically. And by some models I mean typically neural nets. can do these combinations automatically. Other models, you need to do this feature engineering manually. And the example that I like probably, let's do a deliberate that example. We worked on a very interesting problem that we solved with a help of regression. It's modeling response for Chinese medicine. So that's actually a nice example to see how we can, what nonlinear transformation of features may do.
Но здесь, если мы добавляем x квадрата, это же сгибает линию.
Линию изгибает в каком пространстве? В пространстве иксов, да. Да, то есть она будет нелинейной в пространстве иксов, но с точки зрения эта функция остается линейной, потому что x2 можем возвать фича, x квадрат можем назвать фича x2, и опять она линейная, и x2. Ну, а вообще-то она называется линейной регрессией, потому что она линейная по коэффициенту. То есть фичи сами могут быть что угодно, потому что это сейчас колонка числа. Какая разница, мы получили эту колонку, там, беря логарифм, или там, беря квадрат, или беря куб, или еще что-то. Это всего лишь колонка чисел. Линейная регрессия, потому что она линейная по, функция линейная по коэффициентам, по которым мы минимизируем проблемы. То есть наши неизвестные коэффициенты в данном случае.
Вообще это все оптимизационные задачи, да? Это поиск этих коэффициентов, только позволяет минимизировать.
Конечно. Это для любой модели. Поиск параметров модели, в общем,
это самое, да, то есть поиск для того, чтобы потом,
да, чтобы найти коэффициенты, которые минимизируют ошибку. Да. Вот и все. Ну а как только мы начнем, что такое коэффициенты для decision trees, что такое коэффициенты для нейронной сети? Вот уже начинается, тут уже какие там коэффициенты в этих деревьях решений, где они там эти коэффициенты есть.
А вот это вот то, что мы разделили урбан и урбан на два отдельных столба, я только сейчас убился. 0,0, вот это тормозили только сейчас. Что это позволяет же разные бета применить каждому столбу. Да. А когда мы составляем ордер, то мы сами решаем, как бы, мы сами влияем на эту бета. Бета остается одна, но мы как бы...
у тебя, с другой стороны, ты добавляешь больше иксов,
больше иксов, больше бета.
У тебя уменьшается degree of freedom. У тебя квадрат будет расти, потому что ты добавил больше.
Вами больше degree, потому что да, 0,1. То есть если
ты добавляешь больше измерений,
у тебя фича единица, он просто взял.
Мы с кем ты разговариваешь?
Я тут сам.
А на самом деле...
Continue.
So coming back to feature engineering. So an example that I would like to give you. So what at some point we worked on modeling the patient response to different Chinese medicine. So target variable Y is the response of the patient to the Chinese medicine. So what's different between Chinese medicine and Western medicine? What they do in Chinese medicine, they mix different herbs together, and after that, so typically we have choice of around 30 herbs, this recept trap. So we mix those together, and after they treat different diseases. And they can measure the response of the patient, whatever that means, how patient is responding to Chinese medicine. So what we wanted to do, we wanted to design new mixtures, and for that we had to understand how response is related to different Chinese medicines. And that's a standard linear regression model, beta 0 plus beta 1, x1, where x1 is the herb number 1 that you mix, plus, and so on, plus as you have around 30 herbs, your model can be like that. The thing is that basically the reaction, the response to the medicine is not necessarily linear. So it can be quadratic as well. So what you can do, you may need to introduce additional features to square everything. That's 1 squared and so on. But after that, again, we figured out that herbs can interact with each other. So you essentially need to introduce all combinations, x1 multiplied by x2, x2 multiplied by x3, and so on. So because herbs can basically either enhance the effect of each other when those are together, or the opposite. Now, how many variables you have already if you do this? So we had 30 variables initially, now we need all combinations, so 30 squared. So now you already have around 900 features in your model. The thing is, you may also look at the interactions of 3 or more terms, if you want. x1 multiplied by x2 multiplied by x3. So you may look at the third order effect, and so on. So your problem can easily become a really large problem. But even if you stop here at the quadratic effect, you already have 900 features. And that's where these non-linear transformational features make sense. You need to introduce quadratic terms. Again, after you just call this whatever feature 31 instead of x1 squared and so on, and it's just we are back to the linear regression. But another issue that appears there, okay, probably 900 features is too many. You want to know which of those are not important. And by not important, we would like to think, can our model somehow assign a zero coefficients to those features which are not important? Or not? So that's what we'll be doing next. But again, one lesson from this, squaring the features makes sense. Other nonlinear transformations of the features may also make sense, the cube, logarithms, and so on. That's part of the feature engineering, but you need to understand whether that feature engineering is necessary, whether it makes sense to introduce it or not. And that's problem dependent.
But to put square for x1, it is, I mean, it does not replace the situation when you want to test x1 multiplied by x2.
Of course, that's going to be another feature, that's going to be feature 32 and so on. Yeah. But again, all what is necessary to remember, x1 squared is just a column of numbers. And you can call it feature 31. x1 multiplied by 2 is another column of numbers. You can call it feature 32. That's it. So you can always write your model in the form of, in that form that we were writing. So theta transpose multiplied by x, where x is already a transformation of any other features that you have. Okay, and yeah, so all those things are just, yeah, if the beta is greater than 0, positive association, less than 0, negative association, 0, no association, and so on. Yeah, all this nonlinear transformation that I just discussed, you can always do nonlinear transformation of features and after call it another feature. So x1, x squared is feature x2, x3 squared, x cubed is feature x3, and so on. And in that case, of course, when you plot it in the space of x, that's going to be a nonlinear curve, not a line. But it's still not linear regression because in this space, it's always linear, both in betas and in x's. So when we already have done transformation of the features, it's still a linear function. But what's even more important, it's always linear in terms of the coefficients, the function itself.
But so why it's not linear here?
Because we plot it in the space of x, and you see it's x squared here, x cubed. So when you plot it in the space of x, of course, it's not a line, it's a curve.
But not on the basis of the features.
Yeah. So that's why actually some people will call this a non-linear regression. Even so, this term is really misleading. It's still linear regression, but just these transformed features. Of course, yeah, when you plot it in the space of the original features, it's going to be a non-linear curve. That's why the name non-linear regression comes from, but because it's misleading, I prefer not to use the term non-linear regression. It's still linear regression, but with engineered features, which are non-linear transformations of the original features. But if you hear the term non-linear regression, yeah. Okay, so there are all these measures of the accuracy for the linear regression. What would be important for us is the mean squared error. That's our original error that we used, and that would be our main basically error measure, mean squared error.
It's RSS. It's the same?
Sorry?
It's the same as RSS?
No, recess is something different, I think. What is recess?
The residual sum of squares.
No, residuals are the errors. So the error is epsilon that we denote. Those are the residuals. So residuals are the errors for every example. And this means that there is an overall error. And typically
It's a sum.
Yeah, it's a sum, but I think typically by residuals we call the absolute values of difference from the squared. Or if you want to remember, residuals are those individual squared errors, which example of those are?
Here you have residual sum of squares multiplied by m. So it's the sum of residuals squared. It's residual sum of squared. Mean squared error is this residual sum of squares multiplied by 1 by m.
Okay, so residual from this here, residual looks like it's an absolute value of the error, and after you square it and sum up and you get the mean squared error. So residual is this. That's residual, for example, 1. That's residual, for example, 2, the absolute value. After you square that residual and sum all that, you get the mean squared error. Okay, yeah, thank you. That's great. So some of these things I never really thought about the names.
And mean squared error is divided by m. So
Yeah, the mean squared error is typically divided by m, so you get the average. That's why it's mean squared error. So sum of squares divided by m, you get the, so this is squared error, divided by m, you get the mean squared error. And in some cases, for easy interpretation, people take the square root of this, so it's called the root mean squared error. Yeah. Because otherwise the numbers are getting huge because it's squared. So you get huge numbers and not easy to interpret the error, so that's why in many cases people take the square root. That is because root means squared error, and it's easier to interpret because it has the same units pretty much as the target variable, not the squared units. Okay, and now we come to a very difficult topic, which is called the bias-variance trade-off, which is...
It's already biased. Difficult. It's not difficult.
So if you are able to understand this, because it's the same for every machine learning algorithm, unsupervised machine learning, sorry, for unsupervised it's different. So this, and that has to do with, of course, interpretation of the error. So now we need to start thinking about the error, more than we were doing here. So when we think about the error, what do you mean by error? What is the true error of our model? True error. Wow. And basically what it says, on which data we should measure the error. So when you measure the error on the data that you fit your model, that you compute your coefficients, it's a bit misleading. So when you measure the error on the training data, the data that you use to compute the coefficients, yeah, that error can be quite small because you can overfit to the training data. If you measure error on the test data, that's a better measure of the error. So what should we do initially? We should split our data, our examples, into the training examples that we use to compute the coefficients, the parameters of our model, and the test data that really tells us what is there. We already have the coefficients that we feed on the training data. After that, we get our test data and we compute the true error. So that's one interesting thing. So that's why we pretty much always split our data set into a training and test. So let's say that we have 1,000 examples from 1 to 1,000. So what we can do, we can use first 800 examples for training. By training, I mean computing the parameters of our model, computing the coefficients. And after when we know parameters, we can use these remaining 200 examples, our test data, to compute the error, to compute the same mean squared error, but on the data that our algorithm didn't see during the training. Is it okay with everyone, this concept?
Yeah.
So that's error on the test data is much better estimate of the error on the training data, because training data there can be even 0, but we can overfit, and we'll discuss much more what we mean by overfit. So that's the first thing that we will need to do in our with our data set. Split it into training data set and test data set. Typically, it's either 80% training, 20% testing, maybe 70% training, 20% testing, things like that. In some cases, people call this validation data set instead of test data set, but again, doesn't really matter to make that distinction too much. Okay, so what we are really interested in, okay, first thing that we need to do, so this is the concise form for our linear regression as well. So what we can do, we can write this function, probably erase this in the form of the norm function. So we can write down our linear regression. So what we had our matrix x multiplied by beta minus y. So this is the form of what we have. So this is our prediction. Yeah. X transpose x is multiplied by beta minus y. So this is a matrix vector form of our linear regression model. And after to compute the error, well, what we should do, we should square. Yeah, that's a mean square error. So now we can more conveniently write this as a norm function. That's what we have here. So what is a norm function? Okay, so I have it somewhere. Before. Yeah, the norm function. That's another function that we didn't discuss, but let's touch base about the norm function. So it's a special function that is used to measure distances. It's called the norm function. Notation is this norm phi, and the most familiar norm that we have seen many, many times. So the norm of a vector x, so x is a vector. So the second norm, which is also called the Euclidean norm, when we substitute 2 here, so square root sum of the xi squared, yeah? So square root sum of the xi squared. So what it means, we take all the coordinates of the vector x, square those, sum those up, and after take the square root. Anybody have seen this in the past? We all have seen it in the school. Have you ever heard about the Pythagoras theorem?
Yes.
x1, x2. So this is what? x1 squared plus x2 squared square root. Looks familiar? No? No?
Yes.
The same?
Yes.
The same? That's how we computed distances in the school. Distance between point A and point B. Or in other terms, summa quadrata capital or not quadrata hypotenuse, or any other interpretation you want to give it. So this is called the Euclidean distance. So this distance, which is a square root of x1 plus square x1 squared plus x2 squared, and taking a square root, and given this distance. That's just the Euclidean distance. So this function is a norm function, and in this case, it's a norm 2 function, so that's a Euclidean norm, the most famous norm function. General form of the norm function is here, norm p. So we all have seen this, we just never interpreted this really norm function measure distance. Euclidean norm measure distance in our traditional Euclidean space in which we live, in 2-dimensional, 3-dimensional, whatever we use. Maybe we may extend it to the height, not only the width and the height, we can also go.
But it works only if you have a 90-degree angle.
Of course.
In the line.
Well, that's of course this angle should be 90 degrees. Yeah. So that's basically our coordinate system. That's our traditional Cartesian coordinate system, which has of course 90 degrees. So this
It works when x1 and x2 has the same origin. Zero.
Yeah. You can say it that way. This is the region, but of course you can move it anywhere. As always, we do with vectors. You can interpret this as vectors, vector x1, vector x2, and say this is the vector spaces. Doesn't really change much. It's the same mathematics, just slightly different interpretation, the same visualization. That's actually how we sum up vectors as well. And compute the length of this vector. Okay, so this is the second norm. That's the Euclidean norm, the most famous norm. But that's a function. Norm is a function, just a special function that is very useful in data science in general. How about norm 1?
It's some kind of shortcut.
Yeah, norm is a special function that allows us to measure distances in different spaces. In the Euclidean space, in the space of norm 1. So what is norm 1? So here is 1, here is 1. It's the sum of the absolute values of the coordinates of the vector x. And coordinates. So, norm function is again converting the vector x into a number, as any function is doing. So, this is the same f of x, that's a function of x, give us the result. Just it's a useful function because, as I said, this is represent the distance. If we get this, represent the distance, another measure of distance. Sum of the absolute values of the coordinates of the vector x. It's not the distance in the Euclidean space anymore, it's another distance. Other norms, another famous norm is the infinity norm. Here, what happens when you substitute infinity? It's not a straight form, you need to take a limit. We are not going to be talking about limits because you have infinities, but what you will get this. Maximal coordinate of the vector is the infinity norm. Another potentially useful norm. But we may have any norm. We may have norm 0.1, whatever. Any number p would work as a general form of the norm function, which is used to measure distances, just different measures of the distance. So that's why basically we can write this down as the second norm. So what we do in this case, so we can rewrite this as, just put it there, as the norm x multiplied by y second norm and square. So we want to get, there is no square root here, so we need to get rid of square root, so we need to square the norm. In that case we square this, so to get rid of the square root. So that's another form. So what we're doing, so this is a vector, and by taking it norm, we are getting some of the squared components. So this is a vector, x multiplied by b minus y, that's the vector that measures the difference in each example between the predictions of our linear regression model and the true values of the target variable. But because this is a vector, when we take the norm, we unroll it into the sum of the squared components. Again, another way to write down concisely the linear regression function. So that's what I mean. So this is our error. Now, as I said, we are really interested in the error. So what happens when we work in our regression? So we compute the coefficients of our model on the training set, and that is the interesting to measure the error on the test set. That's why we have x tilde and y tilde. So x tilde and y tilde is the training set. X and y is the test set. X and y is the training set. But x tilde and y tilde is the data on the test set. So this will be the true error, the prediction error that we need to compute. So we feed these coefficients on the training data, x and y, and after that, when we know the coefficients, we can compute the error in the test data by substituting the features from the test data x tilde and the target variables from test data y tilde. Sounds complex, I know. You'll need to look at this a bit more. So this true error, which typically is called the prediction error on the test data, that's why it's x tilde, can be decomposed into three components. And we'll see how and why. The irreducible error, that's the error that we cannot reduce at all. So we have all our features, we did our feature engineering, but there is still some non-explainable portion of the variable y, of the target variable. It almost always exists. There is still some stochasticity or something that we cannot explain. And after there are two other components, which are called bias and the variance, and we'll see how this decomposition happens of the total prediction error. So three components of prediction error. This we cannot reduce, so nothing that we can do about it. These two components we can see and play with this and see what we can do. How to get this decomposition? So this decomposition, which is also called the bias variance trade-off. I have a slide, about that. Okay. So, these decompositions comes from the definition of the variance. Variance of a random variable y is what? So, the definition of the variance. So, variance is the expectation of the y minus expected value of y squared. So that's just the definition of the variance, nothing more than that. So what is the variance? It measures spread around the mean. Remember yesterday, spread around the mean. So this is the mean, this is spread of each around the mean, we square it and we take the expectation. That's the definition of the variance, written in the modern science form. Y is a random variable, whatever it represents. After that we start unrolling this formula. So we unroll the square. So we get the y squared minus 2y multiplied by its expectation plus expectation of y squared. We just unroll the squares, and after that, okay, so the expectation of the y squared is here. After that, so we basically move the expectation into here. So here is we have the expectation of y multiplied by expectation of y, and here we have the expectation of the y squared. And after that, what happens? This is here, this is there, and this is.
This is the step number 3 is not clear. There's,
yeah,
when we transform 2y multiplied by expectation of y, then we interpret that into 2 expectation of y multiplied by expectation.
So this is not clear, or this is not clear.
The third line.
Third line. So what we do here?
So
the expectation of the sum is the sum of the expectations. Yeah. So we take the expectation of this minus expectation of this plus the expectation of this, because this is already the expectation of the expectation is the same, so we leave it here. So here, when we take the expectation of this term,
so we take off brackets. That's what we do.
Yeah, we take off brackets. So we need basically the expected value of the sum is the sum of the expected values. So we basically can rewrite it as the expected value of this component, expected value plus expected value of this component plus expected value of this component. Yeah? So expected value of this component is, that's what it is, expected value of y squared. The expected value of this component, so here is already the expectation, so now we need to just take the expectation of y, that's what appears here, that's already there, minus 2 remains, and the expectation of the expectation is the same, so this stays as before.
We take 2 out of the expectation.
Yeah, and after that you see this is minus 2
doesn't matter when we
of this, and this cancels out, so we get minus 6. This minus 2 plus 1, we get minus 1, so we get that. We can do it one more time if you want. So all what we need to do when you have the expectation of the sum, it's the sum of the expectation. So let's expectation of the sum of random variables x plus y is equal to the expectation of x plus the expectation of y.
But why do we take expectation? Because in variance it's just variance.
That's the definition of the variance.
It's just variance from the average, not expectation of the variance, isn't it? The variance is.
Variance is, you see, so variance is the expected sum of square differences between our random variable and its mean.
And its mean, yeah.
That's the definition of the variance, nothing more than that. And after we start unrolling this term until they are here. So this is the transformation of this term using the standard mathematics.
Now we look for this train or this test?
Well, that's come to that.
Okay.
So as soon as we understand that this is equal to this, we go to the next step.
I don't understand. Why don't we take explanation for the variance? We take the value minus average value, we put it into the square, and then we take a sum of it.
Yeah, in the discrete, if your variable y is discrete, expression is the sum. That's what it is.
What is this expectation?
Yeah, so what we had yesterday for the formula of the expectation, or I can rewrite this as a sum if you want. So if our variable y is discrete variable, so that's what we have. We have this sum instead of the expectation. If y is discrete, and inside here we have this minus.
So this formula works not only
minus the mean. And yeah, so that's what it is. So So in the discrete space, that's what it is. Yeah.
Expectation is somewhere, yeah? Some kind of
Expectation is sum in the discrete space. So if your variable y is discrete, that's a sum. If your variable random variable y is continuous, that's expectation. So it depends whether you work with a discrete distribution or with continuous distribution. So yeah, it's easier to understand discrete distribution.
This is a general formula.
It's a general formula, yeah.
And that one which we use.
That's when your y has discrete distribution, which we typically plot as this bar plot, yeah? And that's a discrete distribution. But normal distribution is continuous distribution, so we know the exact of the curve. And that's basically a different interpretation of the probability. So here we need to compute the area, here we just need to basically compute the number of cases in each of these, this and normalize to the total number of cases, we get the area. But that's all related to, we always typically discretize. So remember in school when we had to integrate or something, when we integrate, we discretize and compute the integral, all these rules of integration based on discretization. So that's exactly this projection. So if you need to approximate anything continuous, we do the sum of the discretized intervals. That's the approximation. So when we have to approximate the function, we discretize and we get this. So when we have to approximate this function, we do this. Yeah? That's going to be approximation because these are not exactly. And after all, when we can improve approximation by taking this instead of this and blah blah blah. Yes. If y is a discrete random variable and instead of continuous, this is a sum. Any other questions how we got from here to there by unrolling the formula for the variance? And now, so we rearrange this formula. So we put this on the left side. Expectation of the y squared is equal. So we put this and that on the right side. Is equal to this plus the variance. And this is really the decomposition into the bias and variance. So this term is called the bias squared, and this is the variance. So now, what is the meaning of this random variable y? Well, this is the difference between the predictions of our model and our target variable. That's the meaning, that's our error. Our variable y is the error. And why it's y squared? Because our error is the squared error. That's why it's y squared. So this is the meaning of y. Again, difficult to think about the error in these terms, but in machine learning, our error of our model is a random variable. Yeah? Because we don't have access to complete information. It's a random variable. So for random variable, we derive this formula, that the expectation of that random variable squared is sum of these two components. This component we call the bias squared, because it's squared, and this is the variance. This is the variance, or we can derive it as the definition of this variance. Now, let's try to project this formula into our machine learning algorithm. So what is happening? Let me just write it again, and we'll need to look and explain. Those things are difficult, as you see, especially for the first time. So what is this? So the expectation of the error. So we substitute for the y, so what our model predicts, minus our target variable, or this notation. This is a true model that we know, that we don't know, and it's represented by our target variable. So our target variable is equal to our hypothesis function of the features.
Why the expectation of y into the square? This I don't know.
Because we work with the squared error. We work with the mean squared error. So y is the difference between our model predictions and the target variable, and to represent this error, we need to square this. So that's why it's y squared.
But it was actual value minus expected value. and here we change the order. It was y eta minus y with hat to the square.
Yeah, okay, so let's write it and see. So this represents the difference between what our model predicts and our target variable, yeah? Some people call it true model that we don't know. Governed by some function, that's a true y, we only see y, we don't see this unknown function, and this is the function that we use for predictions, which is not necessarily the true function that governs that process, but that's what we use in our machine learning. Now, if you don't want to really talk about the true function, we can read it as this. Now, this is the difference between what our model predicts and the target value. We said that we work with mean squared error, so this difference should be squared, yeah?
It's the target y we take from test data set.
So target y, we take, okay, before we go to the training test, this is just target variable, this is the model that we fitted that predicts our target variable. And this is the difference, and after that we converted this into the error by squaring this, squaring this and taking the expectation, or the sum, as we call it, over all examples from 1 to n. So this is exactly this term. This is exactly the term representing our mean squared error. This is MSE, and this is the same, that's MSE. Mean squared error. Remember, so mean squared error again, the difference between the predictions of our model and minus the target variable, we need to square, we need to sum up over all examples. And again, so the sum is the expectation, that's why it's called the mean squared error, expectation across all examples that we do by the sum. If you want, we can do 1 over m here. And after this, y represents this difference, and of course it's squared. So y is just a random variable representing this difference. Now, we said that we can decompose this into two terms. The bias and the variance. Now let's write it down. What is the bias? Let's substitute y there into this formulation. So it's equal to sum of these differences minus y and this square this. Yeah, that's our bias squared.
But why it's bias?
Sorry?
Why it's bias?
Why it's called the bias?
Yeah.
Good question. Don't know. Okay, no. So bias is another name for the error. So when we say that somebody is biased, we say that somebody, okay, it's not exactly the error. It's some sort of error, special type of error, I guess.
I mean that when we say that the sampling shall not be biased, yes, so it's clear. But here bias, it's actually not that biased, yeah, but it's different, yeah. So here it's not that somebody.
So, in my opinion, the easiest problem to think about the bias is the error on the training data. So, that's what the bias is.
And what on the test data?
And this is the variance on the training data as well. But that, remember, due to this decomposition, bias plus the variance plus this unknown, give us the prediction error. So the sum of these two. The problem is, we want what we want again. Another probably explanation. So let's try this thing. So the prediction error that we care about is on the test data, yeah? But we don't have access to the, ideally you want this. So it consists of the bias on the test data plus the variance on test data plus the reducible error. The problem is that we don't have access to the test data during training time. So what we can do, we can approximate the prediction error by taking the bias on the training data variance on the training data, irreducible error, which is just constant number, and give us some approximation of the prediction error on the test data. So this, we take this for the training data because we don't have access to the test data at the time of training. We take this at the training data because of the same reason we don't have access to the test data during training. This concept is irreducible in any case, we don't care about it, we cannot do anything about it, and then give us an approximation of the prediction error on the test data. So that's what we want to do. We want to do, can we do something with the prediction error on the test data during the training phase of our algorithm? So that's why we try to represent this as a sum of two components, and these two components we can try to play with those during the training phase of our algorithm. So in the hope that when this trade-off between these two components during the training is playing, so we can get a small error on the test data. And that's what we'll be doing next. That's difficult to understand. We'll probably need a couple of times to really digest it in your head.
Okay, so this is how we, let's say, want to assume what will be the minimum error on the test data, but using the train data.
Yeah. So we want to arrive at the smallest error at the test data by playing with these two components of the error on the training data. That's the idea. But the first step before that to understand why really we can decompose the error into these two components. And that's what this formula is saying. So we can, this is equal to this, so we can really decompose the error into two components, the bias and the variance. And after we can start playing with those during the training phase of the algorithm. These two components and see what happens with the prediction error on the test data in that case. So this is our bias squared plus the variance, which we can also write down as the sum of this minus the expected value of that. Just not going to rewrite this one more time. So the interpretation.
I was just going to ask you that question, the interpretation.
Well, that's what we will be talking about for the next 2 hours, interpretation of all this.
Yeah,
From different.
But generally speaking, though, does this come about because there was an understanding of what bias and variance looks like in different kinds of data and different kinds of sets? Like there's kind of known rules of thumb about what these things are going to look like in different types of problems?
Yes.
Okay.
So for different
So that's why we're
types of functions that we are using in machine learning, how those look like. So
that's the utility of decomposing this, is that when we have into our situation, we know we want
That's right.
one or the other.
That's the idea of decomposing the error into components and playing with these two components to reduce the overall error on the test data. But we want to play with these two components during the training, on the training data.
Is any good graphical?
We'll come to that, yes. Where you will see probably another 3 explanations of this concept in the next 2 hours. Now, so what is bias? Well, that's what we have written. So the bias is this term, the difference between what our model predicts on the training data and the value of the target variable, summing up all the examples, squared. So this is just, if we write it down in our terminology, this is just this computed on the training data. So what is variance? Now we need to figure out what variance means in the context of our model. What is the variance? So the variance is, the meaning of the variance is here. So again, bias. Bias tells us how much predicted values differ from the true values. How predicted values differ from the true values. How predicted values differ from the true values. The variance says how predictions made on the same value vary on different realizations of the model. So how we can interpret the variance? You slightly change your inputs, your features, and you see how much the target variable changed. That's what it is here. So you slightly change your features, and you see how your target variable changed. So if you slightly change your features and your target variable changes a lot, that's a large variance. If you slightly change your features and your target variable changes by a little, it's a small variance. Everybody with me? That's a variation of the output of the target variable. So what? Now let's first understand the extreme two cases. So what is the smallest possible variance?
0.
0. When do we achieve the smallest possible variance? What should be the values of our coefficients beta in our regression model to have 0 variance?
1.
0.
0, exactly. If all betas are 0, we have 0 variance. You change input any way you want, the output doesn't change. It's always constant. Then all betas are 0. Everybody with me? That's what we have. That's the extreme case. Variance is 0. What happens with the bias when the variance is 0? Is our model predict anything useful?
No.
No, bias is huge. That's a huge error on the training data because all our coefficients is 0. So our model predicts some constant number, which is useless. That's a huge bias. Extreme case. Let's say so what happens when the bias is small? What happens with the variance?
Increasing.
What are the values of the coefficients beta when our bias is small?
Positive. No, with values.
Are those large or small numbers? Of course, large numbers.
Right, but it's two extremes, I think, yeah, so.
Exactly, two extremes. So, variance is 0 when all the coefficients are 0, all betas are 0. In that case, the bias is huge. The error is huge on the training data. In the extreme case, when error is small, the variance is huge. What it means, the coefficients beta are huge numbers. Can we do something in between? Can we have some intermediate values of the bias and the variance? And if yes, how? How we can find those?
Minimizing the function of error.
And remember, all what we can do, we can play with this coefficients beta. So coefficients beta are our decision variables. To do this bias variance trade-off, all what we can do, we can try different coefficients beta. But we need to do some way to do it systematically. And that's what will come next. How we can systematically work with these two components. And that is, so before we started talking anything about bias, our regression model looked like this. So we are minimizing the sum of the square differences, now written as a norm, with respect to the unknown coefficients beta. And that's what we now call the function f1 of the beta. So this is the bias term. Now, when we want to play this variance, so how we represent the variance? We represent the variance, and that's exact for linear regression, only approximate for logistic regression, by the magnitudes of the coefficients beta. Yeah, the large values of beta, that's a huge variance. Beta is equal to 0, that's a 0 variance. But how we can collapse? So beta is a vector. How we can collapse that vector into a number representing variance? We can make the norm function, as we discussed. The norm of a vector collapses the magnitudes of individual coordinates of the vector into one number. But the question is which norm to take. So where is all these possible norms? P. P can be any number. So which norm function we should take? In this case, you know, for the bias, it's just the Euclidean norm. That's because we use the mean squared error. That's the Euclidean norm. How about this? Minimizing the variance. Minimizing the norm of the vector beta.
Beta. Oh.
So now let's think about the design. So now we are adding the second function to our problem formulation. We want to in addition to minimizing the bias, we want to minimize the variance. But we need to choose the appropriate norm for that. We can be allowed to choose any. Now, as we are minimizing this function, so what are the properties of this function that we wanted to satisfy? Again, that's the third time that we repeated it yesterday, we repeated it today. What are the properties of the function we would like to hold when we are minimizing that function?
Continuous.
Continuous. Let's write those one more time because we'll get to those. Oops, sorry. Every time. So continuous, everywhere differentiable and convex. Now let's check different norms. Let's check different norms, different pieces. Let's check which of those functions are continuous, differentiable, and convex, which of the norm functions. And let's start with norm 0. Norm 0 is a special function which is known as cardinality, so it's a sum of the coordinates of the vector x to the power 0, which is informally called norm 0. So x to the power 0 is equal to 0 if x is equal to 0 and equal to 1 for any other x. Yeah? Any number to the power 0 gives you 1, except for 0 to the power 0, which gives you 0. Everybody with me? Now let's plot that function. Norm 0. So, when it's 0, we get 0. Yeah? When it's any other number, we get 1. So this, excluding this, we get this. This is how that function looks like. Norm 0 function. Is it a good function?
No.
Oh, it's immediately discontinuous. You see, it discontinued at 1. Or at 0, sorry. It's immediately not satisfying the first property. So we are not going to choose norm 0 because it's immediately discontinuous. So of course it's non-differentiable as well, and it's not convex automatically because discontinuous functions are not convex, cannot be convex. And of course, at the point of discontinuity, those are not differentiable. Now let's write norm to the power whatever, 0.1, 0.2, 0.3, 0.5, and see how those look like. Let's try norm 0.5 or 0.1, those two look the same. That function, if you plot it, and nothing to mention to it, it will look like this. That's any norm between 0 and 1, including 0 and 1, will look like this. Norm 0.1, norm 0.5, norm 0.9. Is it a good function to work with?
Non-convex and
Non-convex, non-differential.
non-differential.
Everybody okay that it's not convex? How do we verify that? Well, we take 2 points, and you see the graph of the function is above this line, so it's not a convex function.
But it is differential.
No.
Oh, it's not differentiable here. It's not differentiable at point 0.
Of course.
Yeah? And again, when we want to show that the function is not convex, all the things we need to find the counterexample. Everybody with me, we need to find 2 points that violate the definition of convexity. That's easy part. So proving convexity is harder, because you need to show that it's convex everywhere. Showing non-convexity is easy, you just need to find 2 points that violate the definition of convexity. Yeah, everybody with me? Okay, now let's try norm 1. On norm 1, we just said that the sum of the absolute values of the coordinates of the vector. That's an absolute value function. You know how it looks like, yeah? The absolute value function. Nothing more than that. Okay, which of the properties satisfies?
No.
Except for non-differentiability at the point 0, it's continuous and convex. Yeah? Everybody can verify this convex, so they connect by the line and the graph of the function is below. So yeah, it's convex. It's non-differentiable point 0, but as I said, there is a trick. You can convert this absolute value function into the piecewise linear function by doubling the number of variables, and it becomes linear, differentiable, convex, very nice function. So there is a trick. How about the norm 2? Norm 2 is just a parabola. Yeah, it's a quadratic function.
This is what we need.
Yes.
Not yet. How about norm 3? Don't stop there. How norm 3 function looks like?
Yeah.
No, that's not. It doesn't look like this. No.
Like this.
Remember, we are squaring the. So we take some of the absolute values to the power 3. Absolute values, not the. So that function will look like this, yeah? Because absolute value to the power 3 will look like this. Is norm 3 convex?
Yeah.
Yes. Continuous? Yes. Yeah, it's probably not differential with 0.0. Or maybe it is differential, we need to check how this looks like. No, it's probably differential with 0.0. Yeah. Okay. How about norm 4, norm 5? All those are going to be convex. The problem is, or no, the problem is, that all other norms, norm 2, norm 3, norm 4 will look very similar to each other. So why to go to the power greater than 2, because those functions look very similar. So it doesn't make sense to take the norm with the power bigger than 2, even so it is going to be convex and nice. Just why to do more computations if the power 2 is already good enough. So the real choice that we have is either norm 1 or norm 2. All other norms are either non-convex or just redundant, as norm 3 and so on. So the only choice that we have here is either norm 1 or norm 2. And we'll need to check both. So the next step is, we decided about the norm. We can take this norm 1 or norm 2. But now what we have two functions that we want to minimize. Function f1, the bias squared, and the function f2, the variance. We don't know how to solve optimization problems with more than 2 functions. That's a multi-objective optimization problem. So how do we do that? So far we talked only about the algorithms where we minimize one function. Now we need to minimize 2 functions. So we need to figure out, are there any algorithms that allow us to minimize multiple functions? And those are called multi-objective optimization problems. Now we need to talk about multi-objective optimization algorithms in order to be able to solve this optimization problem.
But on graphic it will look like conjections of 2 graphs.
It will. Yes. We'll get to that. So now, again, we'll talk about the algorithms for solving multi-objective optimization problems. Just in general, this type of algorithm, when we are going to work with 2 objective functions, called regularized regression. Instead of regression, called regularized regression. If we choose norm 1, it's called lasso regression. If we choose norm 2, it's called ridge regression. We can also combine norm 1 and norm 2. In that case, it's called the elastic net regression. But we'll not get to the combining norm 1 and norm 2. And the idea is, when we use regularized regression instead of the traditional regression, what we can do, we can reduce, as I said, the error on the test data by playing with this bias variance trade-off. Because you see, we have 2 functions we need to minimize. There will be a trade-off. So one function is big, the other is small. And not the opposite. So and there is all in between. So by solving this multi-objective optimization problem, we would be able to compute the trade-off between these 2 functions, the bias squared and the variance. And after that, when we know this trade-off, we should be able to choose a point on the trade-off that gives us the smallest error on the test data. But the trade-off we are computing on the training data, because we don't have access to the test data during the training phase. So regularized regression is essentially introducing the second function, minimizing the variance, that's why it's called regularized regression, on the training data in order to reduce the error on the test data. Sounds complex. Again, that's why we will be repeating this many times, looking at the graphs, doing the computations, looking at examples, just step by step. So far that's the idea. For that, we have to decompose the error into these 2 components in order to be able to play with these 2 components separate. Okay, next step, let's try to solve this multi-objective optimization problem. So what is multi-objective optimization? In multi-objective optimization, instead of minimizing one function, we are minimizing multiple functions, f1, f2, and so on. And typically when we work with one objective function, we work in the decision space. So the decision space is the space of our variables, x1, x2, and that's a feasible region. In multi-objective optimization, we prefer to work in objective space, in the space of objective functions, f1 and f2. And what we do, we take every feasible point, x1, x2, substitute, compute the function value f1, compute the function value f2, plot it here. And we get this feasible region Z in the objective space, in the space of objective functions f2 and f1 that we would like to minimize. Now, if we have our multi-objective optimization, so f1 is the bias, R squared, that we will minimize, and f2 is the variance, that we also minimize. And let's say we have these feasible regions, and we have different possible solutions that are feasible. So, if we compare the solution A to solution B, which one is better? Again, remember that we would like to minimize both F1 and F2.
B.
So B is better, because when we move from A to B, the function F1 is getting small and the function F2 is getting small. What functions are getting small? Of course, B is better. If we compare B and D, which one is better?
D.
D, because of course, yeah, when we move from B to D, you see function F1 is getting smaller and the function F2 is getting smaller. Agree with me? But what happens when we compare solution D and solution somewhere here? Which one is better?
Depends.
None is better, because when we move from this to this one, function F2 is getting smaller, but function F1 is getting bigger. So, solutions of the type like D are called efficient solutions. And all of those solutions are on this curve. You see, when we move on this curve, one function is getting better, another function is getting worse. So that's why all solutions on this curve are called efficient solutions, and none of the solutions evaluated is efficient. So none of the solutions evaluated will never choose. We will only be able to choose the solutions here. And this is exactly the trade-off curve between the two objective functions, which is also known as Pareto frontier, or efficient frontier, or frontier of all non-mediated solutions, whatever it's called, or the trade-off frontier. So, and this is the goal. That's what we want to compute in knowledge objective engineering. We want to compute this curve, because all solutions of the curve are efficient. And that's the goal of multi-objective optimization, computing this curve. So, how we compute this efficient frontier? That's the traditional name for that. So, idealistically, we compute it exactly. So it may have some functional form, it may represent some function. But that's difficult. Even so, yes, it has a functional form. Actually, this frontier is a piecewise quadratic function. But we need to identify the pieces, and the number of pieces may be too large, so nobody is doing that exactly. Nobody is computing that frontier exactly. What people do, we approximate the frontier. So let's say that this is the unknown frontier. What we do, we compute this point on the frontier, this point on the frontier, this point on the frontier, connect those by the lines, and we get our piecewise linear approximation of the frontier. Of course, if we compute 100 points, that's going to be a pretty good approximation. That's what everybody is doing. Nobody is computing exactly, everybody is approximating the efficient frontier. Now, the ideas, the algorithms behind solving multi-objective optimization problems is very simple. Convert multi-objective optimization problem into a series of single-objective optimization problems. And we know how to solve single-objective optimization problems. The same as before in the algorithm design. When we need to solve a complex problem, we split it into iterations. And in each iteration, we solve an optimization problem with one objective function. There are two methods for that, the weighted method and the epsilon constraint method. So what weighted method is doing? Assign the weight to each objective and minimize the weighted sum of the objectives. So we have two objective functions, one and two. Assign the weight W1 to the first objective function, weight W2 to the second objective function, and minimize the weighted sum. Again, this is a single objective function now, which we know how to minimize. So the weights represent the importance of each function, and of course weight should be greater than 0, and sum of the weights W1 plus W2 is equal to 1. Now, because of that, what we can do, we can divide our objective function by W2. That's a positive number, we divide everything by W2, it doesn't change the solution. Everybody with me, yeah? So, W1 by W2, we denote it by lambda, W2 by W2, we get 1 here. So, our objective function will look like this. Lambda, which is W1 by W2 multiplied by 1 plus F2. And lambda is the parameter that we can change in order to compute this frontier. So what happens? When lambda is equal to 0, F1 disappears, we're just minimizing F2, and we get the smallest possible value of F2, this point on the frontier. Everybody with me? After that, we start increasing lambda. Set lambda to 0.0001, we get this point. Set lambda to 0.01, we get this point. Set lambda to 0.1, we get this point. Set lambda to 1, 2, and so on, until lambda is set to a very large number, and we get the approximation of our frontier. All what we need to do, we need to resolve this single objective optimization problem by putting different numbers lambda into there. Everybody with me?
Why lambda for F1 but not for F2, or it doesn't matter?
Oh, you need to discretize the space of lambda into numbers that make sense. So you know that the smallest lambda is 0, and the largest is some large number, let's say 1 million. In between you can put as many points as you...
There's lambda on the F1 portion of it, why not lambda on the F2 portion?
Can be on the F2, so you can divide by W1 and then this lambda will be there, doesn't really matter. The frontier doesn't change because of that. In that case, you just will have the lambda equal to 0 here and we will move in the opposite direction to compute the frontier. Doesn't matter.
Only arbitrary. That's not a preference or a choice, it's arbitrary.
Or it's some convention.
Again, under some conditions, yes. And the condition is, if our functions f1 and f2 are convex, the frontier is also going to be convex. If f1 and f2, that's another importance of convexity. If one of these functions is not convex, our frontier may look something like this. There is always a trick, and because we know what can go wrong when we are working with optimization, what can go wrong? Convexity. So if the function, one of the functions is not convex, our frontier may look something like this. When you start computing it with lambda, going from one direction to the other, this part of the frontier you would not necessarily be able to compute. Especially, let's put it go like this. So there are some parts of the frontier that you will not be able to compute in that case. And in that case, yes, it will matter whether lambda is in front of the first function or the second function. But because, in our case, both the bias term we determine and the variance term as a convex functions, the frontier will be a convex function and we wouldn't have a problem. So it doesn't matter whether we put lambda here or there. Again, that's just because we design our functions, bias and variance to be convex. If we were not careful, not we, somebody who thought about that in the past, designed those to be convex. And that's why, again, convexity is important, because otherwise things will go wrong and we'll need to fix those in the algorithms. That's why we prefer to work with convex functions, because in that case, the frontier is also convex. Remember, so if this function is convex, multiplying it by a positive number as a convex function, this is also convex, sum of the convex function is convex, yeah? But yeah, as simple as that. If one function is not convex, well, we may get anything. The frontier will not also be convex. That's all. Thank you, that's always a good question. So otherwise I forgot to explain it that way. That was two good questions. And that's great. The more you ask, the better, because I also tend to forget about some things or not to think about that way. Of course, some questions I may not be able to answer until I look it up. That also happens. Second algorithm, basically what it does. First, completely forget about the objective function f1, just optimize the function f2, and get its ideal value at the first step of the algorithm. At the second step of the subsistence state algorithm, you minimize f1 and you put a constraint on f2. What this constraint says? In order to improve my function f1, I want to sacrifice or sacrifice? Sacrifice, yeah? Sacrifice my ideal value of f2 by a certain percentage epsilon. I want to give up, for instance, 10% of my ideal value of f2 in order to improve f1. I want to give up 20% of my ideal value of f2 in order to improve f1. And now, as you see, 1 is a number, epsilon is a number, ideal value of 2 is a number. We can just collapse that to one number that we call epsilon. And that's what we're going to change to compute this efficient frontier. But now our parameter epsilon is not in the objective function as it was for lambda, it's in the constraint. When we change this epsilon, we trace efficient frontier. Why? So we start with the epsilon equal to the ideal value of f2, which is over here, the smallest possible value of f2 that we computed at the first step. And after that we start increasing epsilon, and the solution is going to be, okay, first let's figure out what is this constraint. What that constraint, the function value is lesser than the epsilon. That's a set. As we know, function less or equal than the number is a set. What we also know, if the function is convex, its level set, as we learned yesterday, is also a convex set. Yeah, that's what we had one of the properties yesterday. So now let's plot it. Just let's plot that set, as we always do. So function value f2 is here, f1 is here. So f2 less or equal than the epsilon. So let's say the epsilon is equal to this number and maybe 20, whatever. So f2 lesser than the epsilon. How that set will look like? f2 lesser than 20. Now everything underneath this curve, yeah? That's what it is. Now, you also want to minimize f1. And this is the unknown frontier. We don't know. So you minimize function f1. You want f1 to be as small as possible, minimizing. And you want to satisfy this constraint. Constraint is everywhere. So the solution will be here, yeah? So this is still feasible, because we're in feasible region, and we cannot move anywhere further in f1, because otherwise we are getting infeasible. So if you move here, you're getting infeasible. So this will be the solution. And after you start changing this epsilon, so when you put the epsilon here, you find this point. When you put the epsilon there, you find this point, and you trace the efficient frontier by changing the epsilon. Again, due to convexity, this is still the same efficient frontier that we got in the previous algorithm, but now the parameter, the number that we are going to change to compute it, is in the constraint instead of lambda being in the objective function. Essentially, these two optimization problems are very similar to each other and give us the same frontier. Questions? Okay, two algorithms to solve this multi-objective optimization problems: weighted sum and epsilon constraint. Yeah, we move this line and we trace the efficient frontier. Now, as we said, we know now two algorithms for solving these multi-objective optimization problems: the weighted sum and the epsilon constraint. The weighted sum and the epsilon constraint. And we have also two choices for the norm of the beta: norm 1 or norm 2. So that gives us four possible algorithms for regularized regression. So the first, when we regularize this norm 1, which is called L1 regularized regression, or Lasso algorithm, we can either solve this weighted sum formulation, this is the lambda here, or we can solve the epsilon constraint formulation with the epsilon here. Nothing more than that, we just derive this. Minimizing function f1, putting the constraint that the function f2 is less than the epsilon. Minimizing function f1 plus lambda multiplied by the function f2. Everyone with me so far? Or when we choose second norm, which is called L2 regularized regression or Tikhonov regularization regression or Rich regression, so the same. So just the difference is we will be using the second norm. Lambda multiplied by a second norm of beta, or second norm of beta lesser than the epsilon. That's all. So now we need to figure out how do we solve these optimization problems. And each of these optimization problems is give us the vector of the coefficients beta. When we start changing lambda or epsilon, we get different sets of parameters beta, so we get different coefficients of our linear regression model. And for that, we can compute our error on the test set. Because we computed the coefficients beta, now we can compute the error on the test set and compare those errors for different values of epsilon, different values of lambda. Yeah, a bit of unrolling, so of course if we can unroll the norm, so the norm is just this quadratic function, this vector transpose multiplied by this vector, and we can unroll the first norm, so the first norm is the sum of the absolute values of the coefficients beta, less or equal to epsilon, so we are rewriting it in our more familiar terminology, getting rid of the norms. So here, the second norm is going to be sum of the squared coefficients I less or equal to the epsilon. So that's what we can stick into the Python solver if we want. And after that, visualizing the results. So now what we want to visualize the solution of this problem, of these problems. Because without understanding it, it's difficult. Now, if we do not, let's say that we only have two unknown copies, we have two features. So we have the only unknown copies, beta 1, beta 2. So only two features, x1 and x2, so that we can plot. And if we don't do any regularization, so we just compute coefficient beta 1 here, coefficient beta 2 there. Now, so what is our objective function? So how our objective function looks like? Our objective function is quadratic function, yeah? What are the level sets of a quadratic function? Ellipsoids. That's how we can visualize minimizing quadratic function. When we don't have any constraints, when we don't have any regularization constraints, that's a solution. That's the point of the unconstrained minimum when we just minimize mean squared error, when we just minimize the bias square. We're saying in both cases for Lasso and Lynch.
Why is quadratic? Because
well, that's a quadratic function. Second norm is a quadratic function. Well, that's how we design it. Mean squared error. Or writing it in a normal term, getting rid of the norm. That's a quadratic function. Now we have constraints. So now let's plot the constraints. So how to plot this constraint? Let's plot sum of the absolute values of the coordinates beta, and we have only two coordinates, two-dimensional space of unknowns. So beta 1 absolute value plus beta 2 absolute value less than some number. How that set looks like? Anybody has ever plotted that? Again, plot everything. Plot everything. Let's do this. So we have beta 1, beta 2. So absolute value of beta 1 plus absolute value of beta 2 less or equal than some number, let's say 1. This epsilon, so it doesn't matter what it is. How do I plot this? Let's say I have 1, minus 1, minus 1. Again, not gonna to, you can verify myself, but that's how this is going to look like. Absolute value of beta 1 plus absolute value of beta 2 less or equal than, in this case, 1. Everybody agrees that this set looks like this. And then we change this epsilon, it's going to either shrink or expand. That's what's changed with this constraint, with this feasible set, when we change the epsilon. So if epsilon is equal to 0.5, we have it here.
but it's filled, right?
Huh?
It's filled.
Yeah, of course, less or equal. So everything inside the set is included in the set. Of course, we want it to be convex. So this is a convex function, as we know, we designed it, that's a norm 1 function, less or equal than any number is a convex set. That's a level set of the function, and that's what we said yesterday. So if this function is convex, that function less or equal than any number is a convex set. That's called the sub-level set. Okay, that's a feasible set for the norm 1 regularization, for the Lasso regression. How about norm 2? So norm 2 is we have beta 1 squared plus beta 2 squared less or equal than some number. How this set looks like? Well, that's a circle, yeah? So that set looks like this. Circle and including everything inside the circle, yeah? And that's what I basically plotted here. So this is the feasible set for the norm 1 regularization, this is the feasible set for norm 2 regularization. Where is the optimal solution? Where the smallest level set of the objective functions touches this constraint over here. So those level sets, and we want to be as close to the unconstrained minimum. So this is a solution where this level set touches the constraint. The same here. So now let's overlay these formulas. So this is our non-regularized regression where we just minimize the bias squared function. In scalar terms, I write it this way because we have only two features and two coefficients. So this is sum over all examples of beta 1 x1 in the example j plus beta 2 x2 in the example j minus the target variable in the example j squared. So those are the basically the level sets of these functions. That's what we plot when we change betas, we get different level sets. Now, and then constrain optimal means this beta 1 hat and beta 2 hat when we don't have any regularization constraints. We just solve this minimization problem without any constraints. That's a standard solution of the linear regression. Now we add the constraints. So the constraint beta 1 plus beta 2 is epsilon. And here, now the optimal solution is here. Of course, when we change the epsilon, this is strings of rows and solution will move. Everybody understand that? Yeah? When the square is extended, the solution will also, the other level sets attaching there, the solution will move. The same here, the circle, beta 1 square plus beta 2 square is the epsilon. The level set of the first objective function attaching the constraint set. So the solution is here. So any questions about this visualization of the regularized regression algorithm?
This ellipse, yeah, so it depends on what? The size?
Well, the size depends on your features. That's a vector of features in every example. Yeah.
But why the size is different?
Well, the size, this is a quadratic function. So when we plot the quadratic function, so what I'm plotting is...
So you have here 3 ellipses, yeah? So each ellipse corresponds to what?
So what I'm plotting here is beta 1, beta 2, and this is the function value for both. So our function is quadratic. When we intersect it with this, so we get the level set. Intersect with another, we get another level set. That's what
so it's,
I'm plotting.
It's all y values, yeah?
Yeah, that's what I'm just remove the dimensionality of the function value itself. So the third dimensionality, I'm just plotting the level sets to make it easier.
So it's for every dependent value we have this.
Well, we have it in the coordinates beta 1, beta 2.
Yes, but this size, yeah, this is slices, it's for every y dependent, yeah?
Of course. You need to sum up all examples, as we already did. It's a sum of quadratic functions for each of the examples. And what we know our features in every example, feature 1, feature 2, and we know the target variable in every example.
Okay.
Beta 1, beta 2 are unknowns. 2 unknowns, which are of course here. So everything else is fixed. Quadratic function with 2 variables, beta 1, beta 2. All the other coefficients will come as numbers. Still quadratic function, and you know all coefficients of that quadratic function. So, and that of course determines the level set that you have. Mm-hmm. Yeah, unfortunately I didn't finish preparing the Jupyter notebook for that, but I will show you what I have after lunch. So because we were exactly in Python, we plot this. And you confirm that this is really the case and I'm not tricking you.
But in statistics we use some already built-in functions, yeah? And all this job was done by this function, all the trivialization.
Oh, exactly. Or you can call the Python library that will compute this. Exactly. You do it in scikit-learn, pretty much. But to understand what's going on behind the scenes, those visualizations are useful, and as always, if you do it manually in Python, for understanding, that's always useful.
I'm just thinking, so it's necessary to do extra, or it's already built in always, yeah? So
everything is built in, yeah. You just need to basically, we'll see how that works in the Python modules as well for the built-in, but in order to understand what's going on there, that's why we go to these details.
It's not black box, but
it's not black box, it's exactly this.
Mm-hmm. For Lasso, this ellipse will always touch. So
exactly, that's a question that I was expecting. So, for Lasso, now, what's the difference between this solution and this solution that we got from Lasso and that we got from Reach?
That's off axis.
Difference of B1.
Exactly. In this case, B1 is equal to 0, yeah? B2 is non-zero. In this case, both B1 and B2 are non-zero. What's better?
Both non-zero.
If the if x1 is in
let's think together. So what's better? Having all betas non-zero or having some betas equal to 0. What does it mean for a beta to be equal to 0?
It means we select one feature.
Exactly, it means that the feature is not selected. Its coefficient is 0. So in this case, what it means that feature 1, its coefficient beta 1 is 0, is removed by the algorithm from the model. It's not important. So what that means, that Lasso algorithm also does something which is called feature selection for us, or variable selection for us. It removes some of the features which are not important. Lasso doesn't do that. Why? Because of the topology. So in most cases, the solution of this problem will be in the corner of this square, yeah? Either this corner or this corner. So some of the features will be 0, some of the coefficients beta will be 0. For the Lasso, for each, it will almost never happen that some features are 0. The chance to get a solution here or there is almost 0. So for Lasso, all features will be important. None of the features will be set to 0.
For each.
For each, for each. So, and that's the difference. Most people will prefer Lasso because of the 3 reasons. Inside the algorithm, Lasso algorithm does feature selection for you. It removes the features which are not important by setting the coefficients beta to 0. This rich regularized regression doesn't do it for you. It doesn't do feature selection automatically inside the algorithm. It keeps all features there because all coefficients beta will be non-zero.
So it's by nature of algorithm, yeah?
Exactly. And that's the advantage, that's why most people will use Lasso.
But all the difference between algorithms is always square.
Exactly. That's the difference how the constraint set looks like, the physical set looks like. Here is a circle, that's why when ellipsoid is touching a circle, and basically when two ellipsoids touch each other, they will always touch it on somewhere here. When an ellipsoid touches a square, in most cases we will touch it in the vertex in the corner. Let's call it in the corner.
So if you run Lasso method, we ask Lasso method to exclude at least one.
Exactly. No, not at least one. When basically, remember, you are changing epsilon. So when you change in epsilon, different number of features will be included and excluded.
Yes.
So and you can do when you're changing the size of the feasible set epsilon. So you know. In 2 dimensions it's not visible, but if you have many dimensions, you will have all sorts of cases. You will have 1 feature excluded, 2 features excluded, 3 features excluded, and so on when you change your epsilon. And you can decide what's better for you. But you still need to incorporate decision. So all what it gives us efficient frontier. It gives us this trade-off between variance and bias. And now we need to evaluate this trade-off by evaluating the errors on the test set, to choose the best solution, the best set of coefficients beta. Because again, remember, when we change epsilon, all what we get different vectors beta, different vectors of the coefficients. Everybody with me? That's it. And after that, we have these different possibilities for the coefficients beta, and we can compute the error on the test set because we know betas. And choose such vector beta that gives us the smallest error on the test set. That would be our next step, which I will which will look something like this. And we'll go through it after lunch. So when we change parameter epsilon, which is here, so this is our bias square, this is our variance, and this is our error on the test set. And we'll choose a point where that error on test set is the smallest. So we'll choose this point corresponding to some value of the parameter epsilon. All of that. That's what we'll do after lunch. That's all what we'll be doing. So we are going to compute this curve and choose the point where that error on the test set is the smallest. Yeah, right. Yes, we are late for lunch. Sorry about that. So for how long? Yes.
Продолжим, так сказать, на полную жизнь.
Надо что-то так.
Да, надо выпить.
Не я это придумал.
Okay, sorry for being late. For lunch, we'll just start later. The lunch.
So what time are we back there?
So we have to finish at 20 minutes ago, yes?
Yeah.
Yeah, so let's start 15 minutes later, yeah? So instead of 2:30 to 45, yeah?